Well, welcome everybody, and a special welcome to Callum, who's going to be joining us from Delivery, and will be sharing um, sharing or telling us all about recommendation systems and giving us a bit of a workshop too. So I'm going to hand over to Callum to tell you more.
Thanks, Miriam. Let me share my screen so you can see what I'm looking at. Okay, can you see that? Someone give me a thumbs up. Cool, nice. So welcome everyone, and thanks for that introduction, Miriam. I'm really thrilled to be here to share a bit about recommendation systems and to run this hands-on Python workshop. I hope you've all been having a good careers week, and there's been some interesting sessions so far. Hopefully you'll find this one interesting and fun as well. So as Miriam mentioned, well, maybe you didn't mention, but I'm a machine learning engineer at Deliveroo. And that means that my day-to-day job is spent primarily building and maintaining models and algorithms that automate and optimize decisions. What that means in practice is decisions like allocating orders to riders, estimating how long it takes your food to be prepared, through to other use cases like detecting fraudulent or bad behavior, as well as recommending items and grocery and restaurant partners to users. And that's the area that I'm closest to and the area that we'll speak about today. As we go through this, by the way, if you've got questions, please drop them in the chat. We'll get to them at the end, or raise your hand at the end of the slides and we can have a chat. So as far as the agenda is concerned, what we'll cover today is I'll introduce what recommendation systems are and share a few examples. I'll touch on the two main kinds of recommendation systems, which are content-based and collaborative. We'll spend a moment discussing how to measure the performance of these systems, which is a really important step, both for models that are in production and running, but also something that we like to do before we launch a model to make sure that it's working to the standard that we would expect. I'll touch on this philosophy that we have at Deliveroo called a bias to simplicity, and I'll spend a few minutes explaining why this is such a powerful and important idea. And then at the end of the slides, we'll switch tracks to this hands-on Python workshop. So if you've just noticed that last dot point, and you have no experience, no exposure, no idea what Python is all about, don't panic. You're very welcome to stay for the slides and then decide whether you'd like to continue on through the workshop component. If you're on the fence and you're not sure if you'll get something out of it, stick around. We'll go through the beginning of the notebook I've prepared together, and then you can decide if you want to have a crack at working through the problems that we'll solve together. To get the most out of it, ideally you'll have had some basic Python exposure or a similar programming language, and even better if you've used or know what pandas is for dealing with data. But again, if you don't have this, don't stress. You're very welcome to stay for as much or as little as you like. So what are recommendation systems? The point of this slide is not to make you hungry, but it has that effect on me. The point is that there's a huge amount of items available on our platform, and indeed any other platform with a recommendation system. But in all likelihood, when a user opens up the Deliveroo app, they're probably only going to be interested in a small number of what's out there. So a recommendation system is all about really trying to identify and pull out that small subset of items that is most interesting and relevant to the users, and then presenting them to them. A few examples of what this looks like at Deliveroo. Firstly, the most obvious one would be the home feed when you launch the app. So we'll lay out this page differently depending on what our models predict you'll find most engaging. And we also change the order in which the partners are shown within each of these slices or carousels. And we do this based on predictions from models that tell us how likely it is we think you'll be interested in what we're showing you. Another example, which is one that I'm more close to, item recommendations on the basket page. So this is where we take another opportunity when you've assembled an order and you're on the basket, and we'll show you here, popular with orders like yours, items that we think might go well. So a garlic naan should go well with chicken ruby or matar paneer. And again, we surface recommendations after this screen when you go to the checkout in a full page layout. So here we're trying to suggest items that we think you'll like or that might go well with your order so that you'll hopefully add them. I'm obviously very biased to delivery, but just to show I'm not a complete lost cause, there are loads of other great recommendation systems out there. Netflix is a particularly sophisticated one. Aside from getting a glimpse into the eclectic combination of tastes of my partner and I, you'll see here a few different types of recommendations. So trending now, obviously those are good candidates for things that people might be interested in, as well as shows that you've seen before. I don't think this will be a surprise to anyone that your Netflix homepage is going to look different to mine. But something that some people might find surprising is that for each of these shows, there's a whole collection of images that could be shown to represent that show. So you might see a different image representing Seinfeld than I do, and the decision of which thumbnail or image to show is again based on predictions from models and recommendation systems. That brings us onto the two main kinds of recommendation system. These are things that you'll learn about if you do any sort of entry-level course or look at any blog posts or notes online about recommender systems. They'll usually divide them into one of these two categories, either content-based or collaborative filtering. Content-based recommendations. These are all about focusing on what we know about items and the properties of items. So by properties, I mean things like the name, the description, the price, any category that name falls under within a sort of structured hierarchy, even things like the color and weight and so on. With all of this information about the properties of items, you can then compare items to one another and make recommendations based on that similarity. Excuse me. So for example, if I was on Amazon and I was looking at this yellow electric blanket, then Amazon would be able to compare that item to everything else in its catalog and surface up these deals on similar electric blankets. And these systems might also generate user profiles based on the properties of the items that that the users interact with. So if you've got a profile that describes what things people have interacted with and their properties, then you compare that profile to other items and try to predict how likely it is that those items will also be interesting. So in contrast to content-based, which really focuses in on what we know about the item through its properties, collaborative recommendations can work without knowing anything about the content of items. Instead of looking at what we know about the items, they measure similarity of items by the interactions of users who like them. And what do I mean by this? So, for example, if I've read and enjoyed Pachinko, and Miriam has as well, and Miriam has also read and enjoyed Crying in H Mart, then the system can recognize that, well, Miriam and I have some overlap in our reading tastes, and I haven't read H Mart, so that is something that I might find interesting. So it can make that determination without actually knowing what the contents of the book are. So the key idea here is that we're using interactions between users and items, and we can use those interactions to either compare the similarity of items or compare the similarity of users to one another. You can get all kinds of systems that also combine these two approaches in a sort of a hybrid system, but I won't go into that because I want to preserve as much time for the workshop as possible. So if we've built a system that can make recommendations, it's really important that we can measure its performance. And this is both in terms of, I suppose, tracking these models over time and making sure that they keep working at an expected level, but also, even more importantly, perhaps, if we've built a new model and we want to try and estimate how well this is going to work compared to the existing one, we need a way of quantifying the effectiveness of these recommendations. And typically when we make recommendations, we're showing more than one option. So we have a collection of items, and then we sort them in order of what we think is most to least attractive. And so a good recommendation system is one that takes the most relevant items and puts them at the top. And we can create a quantitative metric for measuring this. One such example is mean reciprocal rank, which I'll explain in a moment. So in this case, the house black dial I've added, and that was in position or rank 3. So that's not bad. It's visible on the screen. You can kind of see that if that recommendation was in position 6 or 7, I would have to scroll to get to it, and that is definitely not as good. So what is mean reciprocal rank? If I've got 5 separate recommendations that were made, and we lay them out here, we can see that the rank or position of the item that was interacted with in the first example was position 4, and position 3 for the next one, and position 4 again, and then position 5. So the reciprocal rank is just 1 over that number. So 1 on 4, and 1 on 3, 1 on 4, etc. And then the mean reciprocal rank is the average of all these reciprocal ranks. So you can kind of see that if our recommendation system was performing as best as it possibly could, all of these green converted items would be in the top position. The reciprocal rank would be 1 for each of them, and the mean reciprocal rank, or MRR, would be 1 as well. So 1 is the best possible score, and then it just decreases and approaches 0 as these items go further down the list. Back to that point of bias to simplicity. So it's really, really important to start simple with these things. And sometimes really simple baselines, and we sometimes call these heuristics, can be surprisingly effective. And an example of this would be a recommendation system that simply sorts the items by how popular they are. That's what we're going to build in the workshop. We're also going to build a system that ranks items by co-occurrence. And what this means is that we look at what's already in your basket, we look at a history of orders, and we say which items have been purchased with the things in your basket most often. So it's kind of similar to overall popularity, but it takes into consideration what items are in your basket and what they've appeared with in the past. So if you can build a simple baseline, it's really powerful because you'll encounter all kinds of difficulties and unexpected challenges that are around the model and not the model itself. So getting the data in, deploying the model in production, you'll get surprises with edge cases and data. And if you've got a simple algorithm, it's much easier to diagnose and troubleshoot all of these problems and get the whole system working. And then you can optimize the model itself. So it's a really powerful idea that it is well worth leaning into. Cool. That's it for the slides. I deliberately kept this brief because I wanted to keep as much time as we can to do the workshop together. Before we jump into it, let me describe how it's going to work. And then we can also take a few questions before we move into the workshop in case people want to ask questions and they don't want to stick around for the whole duration. So the way this will...
So people start putting questions in the chat if you've got them, and then Callum, if you want to describe what's happening next, that would be great.
Yeah, perfect. So what will happen next is I've got this link which we'll share to a Google Colab notebook, and that'll open up a new page with the task that we're going to try and tackle together. I'll stay in the main call. I'll introduce the problem. I'll talk through the data and how to work with Colab. And then once we've sort of got a shared understanding of what we're trying to achieve, we'll shuffle people into breakout rooms with 3 or 4 others, and we'll work on a warm-up task together. So the idea here being is that in a smaller group, it's going to be easier for you to help one another if you get stuck. And we'll spend, I think, 15 minutes or maybe 10. We'll see how we go on the first task. And then we'll bring everyone back into the main call. We'll have a chat, ask how it went, and I'll go through my solution together. And then we'll rinse and repeat this process for the remaining exercises. So hopefully that makes sense. And I'm going to try to bring up the chat. I'm not sure if there were any questions.
Yeah, no, there's no questions yet. If anybody wants to put their hands up, that's fine too. Or just, Yeah, no questions yet. I mean, one of the things I was going to say is actually I was a bit surprised by those books because I've read three out of five of them as a
Really?
coincidence.
Choice.
Yeah. So, so I haven't read Pachinko, so that is going to be one that's I'll put on mine.
The only one of
You,
those I've read.
oh, okay. Yeah, there you go. Yeah, so yeah, people don't have questions yet. So are you sure you don't have questions? Okay. So so we'll dive into the breakout rooms. I just do need a minute to set them out. Okay, so we said 3 to 4. Uh, um, I just work out how many I need. I think I'll go with 6.
Yeah,
Oh,
I'll share
oh,
the link in
oh,
the.
should I could do that now.
Yeah,
There you
okay.
go.
While you set the rooms up,
Yeah,
thanks,
yeah.
Graham.
There you go. I
So
had it. I already had it on. There we go.
so go ahead and follow the link. Just gonna move this chat out of the way, and hopefully you'll be presented with a notebook
Yeah,
like this.
yeah,
I'll just wait a few moments so that
yeah.
I get
It'd
to.
be good to know that everybody's got access to that link before we open up the rooms, because you might just hit jump in when you haven't got it yet. Yeah, you've got access. Thanks. Who anybody else? Could a few other people just let us know if you've got the link?
I'll see it
Um,
pop up.
and you've got collab working. Brilliant.
Cool. I think everyone's got access, so I'll describe what we're going to do first, and then we'll go into the breakout rooms. So, um, great. Let's build an item recommendation system.
Yeah.
So, bit of a preamble, we're going to build and evaluate a simple restaurant item recommendation system, and it will suggest items to go with your order. And this is just like what I shared in the slides with the screenshots, where you're on the basket page, and we're going to serve recommendations for things that might go well with your order. So just to try and motivate what we'll achieve here, we're going to build this system, and you'll provide an input basket, in this case, regular fries, and the system will come back with some recommendations. So cheeseburger, deluxe cheeseburger, shake, small cheeseburger, and so on. So as I mentioned at the beginning, we'll use a few Python packages to do most of the work for us. So pandas for reading in and exploring the data, NumPy, which will be useful for representing the baskets and recommendations as an array, and I'll explain what that means later. And then we're going to use this sklearn package, which is a popular machine learning library for evaluating the recommendations. I've left some links throughout the notebook for things you can follow up on to learn in your own time, and also these links at the top to cheat sheets that I think will be handy if you're not as familiar with pandas or NumPy as we make progress. Cool. So again, problem repeated, making recommendations. And again, to keep things simple, we're going to ignore everything we might know about the user. And we're just focusing on what is in the basket and how these items relate to each other. And when we think about what it means to make a recommendation, the frame that's useful to think about here is that we have the basket as an input, and then the output of the system is a score for every item on the menu. So we're trying to give those items that we think are more relevant a high score, and those that are less relevant a low score. Cool. So if you haven't used Colab before, everything we've looked at so far is just a markdown or text cell. This is a code cell, and this is what we actually use to write and run the code. Have a go at running this. You can either click the run cell button here, or if your cursor is inside it, you can do Shift Enter and it should run. And that might take a few moments the first time you run it, and then everything else should be a bit more speedy. The other thing we'll do together before we do the breakout rooms, so I'll just show you the data. So we've got 20,000 orders to work with. And if you run this cell, you should have a download bar pop up, and it should download the data. We can see that's worked because if you open up the folder here, you can see I've got this orders.csv. And that's the data that we'll be working with. And then this is how we read the data into a data frame and have a look at the first 10 rows. So we can see that we've got an order ID column and an item name column. So order 1 was just a small fries and cheeseburger. order 2 was grilled cheese and shake, and so on. Not every order is going to just have 2 items. It just so happens that the first 10 rows looks like this. Cool. Before I go on to the first task, has anyone got any problems with running things? Everyone with me so far?
Yeah, maybe put your hands up or something if you've got any problems accessing Colab, or you need a bit more time to access Colab if you've not used it before. Nobody's putting that.
I saw.
Yeah, it's absolutely fine to observe.
Yeah, absolutely. And
Yeah,
I'm relying on people's feedback to tell me to go faster or slower. So so if this is
yeah.
like really boring and you want to go faster, let me know. But if I'm going too fast, please tell me as well.
Sorry to just interject.
Yeah.
I do feel like this is quite above my stations in terms of my understanding of things. So again, I think I'll observe. I'll do chip in when I can, but I feel like a lot of this might go over my head.
Okay, yeah, this absolutely. It's just to kind of get a sense of what you can do with data. So this idea that there's 20,000 orders that give you clues as to what is in people's baskets and where there may be similarities. So yeah, others that have never worked with Python, what we're thinking is by putting you into groups, there may be people that have worked in Python and can kind of talk it through. But if not, you could kind of talk amongst yourself around what you think the exercise is about, or how you've seen recommendation engines work before.
Yeah, and thanks for the feedback to speak a bit slower. I'll do that. Colab isn't working. Perhaps we can jump in your breakout room, Abigail, and help you with that once we do that. Before I do move on, though, it would be good just to check if there are some people that have worked with Python before, because if not, perhaps I can just go through the notebook and describe what's happening. I don't want to send everyone into breakout rooms and then not be able to actually do anything. But if there's like a few people in some of the rooms, then that might be worthwhile. But if not, I'm very happy to just go through the whole exercise together. Just starting to learn the basics. Never worked.
Yeah, I'm getting a sense there's a lot more people that haven't worked. Also, yeah, anybody with Colab and Python experience. Okay, we've only got one so far. Anybody else? It's looking like we might need you to run through it. Hour 2. We've got 3 people, but I'm not quite sure how we can a little with Python.
All new. I expect.
My feeling is it might be better to.
Yeah, I'm getting the sense that it might be more helpful and productive if I just share what is happening in each cell and we can go through it all together, instead of trying to break people up and make sure that there's someone in the group that's used Python before. So let's do it like that.
Yeah, that sounds good. And maybe taking questions as you go.
Yeah, absolutely.
That'd be good. Yeah. Okay, cool.
I think that's a great way to do it, actually. So we can just discuss as we go through, and if you've got questions, please just shout out, and that will be a bit more organic, I think, anyway.
Yeah. People are appreciating that adaptation.
Yeah, no, very happy to roll with that. I wasn't sure what the level would be at, so I'm glad to get that feedback. So it might be worth just taking a step back then if there's a bunch of people here that have never worked with Python. So Python is a very common and probably the most popular programming language used by machine learning engineers. And one of the reasons why it's so prolific is that it's got a great ecosystem of built-in tools and packages for doing machine learning models. So if people here have an interest in, or maybe they want to test the waters a bit with a more technical role, then I think Python is a great language to learn, along with SQL, of course, but Python's definitely a good one. And if I go back to the packages that we imported, so this again is, these are exactly some of those tools that you can just built into Python and you can use them. So Pandas is a popular package for data science work. It's great for tabular data. and grouping, filtering, summarizing data and slicing it in different ways. And sklearn is a more machine learning focused library. And then NumPy is a useful sort of lower level library that has nice abstractions for linear algebra and arrays. So that will make more sense later. Okay, and then I've read the data in, and this just shows us the first 10 rows, so we get a sense for what the data looks like. So with any data set and any kind of machine learning task, before you jump into the modeling, it's a very good idea to explore the data and understand what it is. And by the way, is this large enough for everyone to read? It's a bit hard to tell on my laptop screen whether this is the right zoom level. Does that look clear to you, Miriam? Yes, cool. So how many rows do we have? The way that we can do this is the name of our orders variable is orders, and we can just ask for the shape. And we can see that there are 53,000 rows and 2 columns. If we want to look at how many distinct items are, then...
Can I ask a question?
Of course.
So the question, before you chose shape, you mentioned how many rows are there. Why didn't you just write rows? Why shape? Is that just the way it works?
Yeah, so the orders variable is a pandas data frame, and it has all of these methods that you can access through this dot operator. And it has a property called shape. I don't know if it has a property called rows. You'll see if we try and it isn't. It tells us that the data frame has no attribute. So kind of it is the way it is.
Okay, thanks.
Cool. So number of distinct items, we're looking for how many unique items there are. And to do this, we're going to look at we need to look at the item name column, because this defines item uniqueness. So I can access the item name column using this syntax. And this will print out that whole column, but we only want the unique values.
Sorry, quick question about the previous line,
Yeah.
Callum. Could you not use len, or is that not applicable here?
That's a great question. Let's see what happens. Yes, is the answer.
Oh.
So the length of a data frame is the number of rows.
Is there like any particular reason to use shape? I mean, obviously you can use both, but is there any reason why?
Mostly just a habit of mine. I think as you begin to work with larger data sets, it's also very useful to know the number of columns and rows. And sometimes you can have like a third dimension to the data. So it's just a habit. But yeah, length is totally fine. So this is testing my ability to present and do the right sort of code, but here we're pulling out the item name column and we're just asking for the unique values. So this just gives us one count for each item. So we can ask for the length of that, for example. And we've got 39 unique items. I'm just going to hide this error. Cool. So that defines the space of items that we're going to try and recommend. In other words, we need to generate 39 scores for every basket because each item needs a score. Most and least popular items. There's another pandas utility here. And in fact, what I might do is just open up this cheat sheet so you can get a sense for how you might actually know what I'm doing and I'm not just doing it. If I open up this cheat sheet, you can see it'll give you a whole bunch of data wrangling techniques, and it will lay it out visually. So for example, reshaping the data, if you've used a spreadsheet, there are all kinds of equivalents for doing those operations, method chaining, queries. I won't go through this in detail, I just wanted to make you aware of it. And in this case, if you want to look at the most and least popular items, then we just need to count the number of times each item appears. And again, this is me sort of just knowing, because I've done this a lot, what the name of this is, but you could look up the docs, you could Google it, you could ask ChatGPT, and it will help you find what functions you need. So the cheeseburger is the most commonly ordered or most popular item. We've got 7,698 orders, and it just decreases. We've got the shake in position 2. It goes all the way down to the bacon and egg sandwich, which is the least popular item. Cool. So the final task here to explore the data is to look at the distribution of basket sizes. This is a slightly trickier task because this is not just something that you can read straight from the data. You have to aggregate the number of items within each order. So we want to look at how many baskets there are of size 1, how many baskets there are of size 2, and so on. And again, you could look this up and you'll find that there's a group by method. We can group our data by the order ID, and we can aggregate the rows and ask for the count. So yeah, please do follow along and type the same code and make sure you get the same results.
So sorry to interrupt. This is really going to show my inexperience, but what does aggregate mean again? I think you did explain it.
Yeah, all the questions are good, no stupid questions. So ag is short for aggregate, and it will, after this data frame is being grouped by order ID, it's going to sort of collapse everything in that group into one row, and ag tells us how we're going to do that. And in this case, we're just counting the number of rows. There's a good chance this won't work though, because I may have remembered it wrong. Indeed, I have. Is it group by? It is group by without the underscore. So now we can see order 1 had 2 items, order 2 had 2 items, and so on. We get 1 row per order now instead of 1 row per item. So that's one part of this problem. I haven't noticed this button before. Let's see what happens if I click it. I was going to write the code for this, but if there's a built-in, oh, look at that. This is almost what we want, this distribution, but it's not quite in the sort of format we want it. So I'll show you how to write the code to produce that chart. And here I'm going to cheat and look at, oh no.
Another question.
Yeah.
Hi, sorry, I just keep getting errors when I'm writing the same code. I don't know if it's something that I'm doing on my side.
Yeah, what's the error that you're seeing?
It's saying name error, trace back most recent call last, and then it's not really like, it's saying it's a name error, orders is not defined.
Okay, I think I know what that is. It might be that you haven't run all of the cells before.
I tried to run when you were doing it before, but to be honest, I've never used this before, so I wasn't too sure in terms of what I was doing.
Yeah, this is the cell that you definitely need to run, and I suspect maybe didn't run the first time.
Okay.
Getting the CSV file is a bit challenging, so let me wind back to that step as well.
Okay.
So if everyone can see this cell, if you run this, hopefully you'll get a green check mark.
Yeah.
Let me know if you have some success with that, and then we'll move on to the next step.
Yeah, that's worked for me.
And then what happens if you run this next one?
The next one. Yep, that's green tick.
And you get this output?
Yes, yes.
Cool. Hopefully now when you try to run that other code, you won't get that name error.
Right, okay.
Try that.
So
And Awa, sorry, I don't know how to pronounce your name.
Yeah, I just have a question. This session is recorded. So
Yes, it is.
how is it possible to see later the video?
It will be on our YouTube channel.
Okay. Thank you.
I'm also happy to circulate the solutions after as well for people to study. Cool. So has everyone had some success getting the CSV file? That one's important.
Yeah, give us a thumbs up.
Cool. I'm going to move on to the next bit. but please shout out if you're stuck. Cool. So
Abigail's saying she's still stuck.
okay.
So just following along. So
Sorry about that,
okay.
Abigail. Hopefully we can sort it out maybe afterwards, and you can try run it yourself. Cool. Yep, still stuck, but follow along. Great. So we've got one row per order, and we've got the number of items in that order. That's great. If we want to plot it, I might cheat and look at what I wrote earlier, so I'm not thinking too much on the fly. Plot.hist. Okay. I'm going to copy this and explain what it's doing. So this what we've got being printed out here is the result of this part of the code that I've highlighted. And then we can, on top of that, ask for a histogram, which is the chart that we want. On that histogram, we would like as many columns as there are the biggest basket size. And then I've just specified how big I want the chart to be. That's all this is doing. If I run this, we should hopefully get an error. This should not be basket sizes. This should be, I need to break this into 2 steps, basically. If I were to just remove this code though, it should work. And we've got a histogram. The only problem with this histogram is that the width of the bar is not equal to 1. So it's kind of saying you've got like 10,000 orders that are between 2 and a bit items, which doesn't really make sense. And if we want it to be, each bar is of width 1, so we're saying how many items are there of, or orders are of size 1, size 2, size 3, then we need to break this into 2 steps, and we can say basket sizes, create a new variable, and that's going to be equal to the aggregate after being grouped by order ID. And then we're going to plot that. And this time I can say bins equals the maximum size of the basket. And I've probably missed a comma here. This is all very normal programming experience, by the way. You'll write some code and you'll try to run it and you'll get errors all the time. Tuple index out of range. What have I done wrong? Basket sizes. I'm just going to comment out this line and make sure that it's the, whoops. My keyboard has changed format. Let's go back so I can type it. This hash, by the way, is just a comment, which means that that line I've just commented out is going to be ignored. I don't get an error, so I know that the problem is on this line. And I'm going to check. What's the difference here?
I think there's a dot size on the end of where it says where you're creating the basket sizes variable. I think there was a dot size method or something, a function.
Yeah. Dot size. You're right. Although, is that different to ag count? Ah, okay. Size is an easier way to do what I was trying to do with ag. Let's see how that goes. Thank you. Lovely. There's our histogram. So now we can see that the most common order size is 2, and there's quite a steep drop off. So this restaurant is sort of biased towards pretty small orders. Okay.
How does the size method work? Like, how does that thing work?
Yeah, so size is going to be called on each group. And again, so the pandas package, when you have a data frame and you group it, you'll then have all these different attributes available to you. And part of this will be like just sort of practicing and learning, like here's subset operations on rows. I'm looking to see if there are like summarized data. So we use this value counts one earlier. And unique is useful, describe. There are often many ways to do the same thing as well. And size may not even be on this cheat sheet. Oh, there we go, size of each group. We also could aggregate it with the count function, but I wasn't having much luck with that. Size is the better approach. Does that answer your question?
Yeah, I think so.
Yeah, Amelia, the link to the cheat sheet is in the notebook at the beginning. So this pandas cheat sheet here. Cool. So this just gives us some sense for the overall data picture, what it looks like. It's very important to plot the data before you start building things on top of it, because you might get caught out with, there might be a bug. You might not realize that you've only got really small baskets. You don't have the whole distribution of data. Okay, I'll move on now to another task, or another idea rather, which is how we actually represent baskets in code. So far we've just got this big table of data, but what we really need to do here is have a consistent data structure which lays out baskets and recommendations. And a natural way to do this is with matrices. Whoops, I don't want to edit that. I just want to highlight it. So matrices, which you might remember from high school, we've got rows and columns. The way we're going to use matrices here is we'll have one column for every item and one row for every basket. So here I've got this sort of toy example, this small example where supposing we only had 2 baskets and there were only 3 possible items. So a hamburger, some fries and a drink in basket 1, and then a burger and a drink in basket 2. We can represent that same information in a matrix like this. So basket 1 has every item, so it has a row of 1s. And then basket 2 only has the burger and the drink, so it has a 1, a 0, and a 1. And this is sort of the central data structure that we're going to use from this point on. NumPy is a package for representing arrays, and this is just the exact same thing, but represented as a NumPy array. So this is another package that you'll learn about if you're interested in learning about data science in Python. And so you can see we define the first row using these square brackets, and then we define the second row with these square brackets, and then the whole thing is wrapped in square brackets. And if I run that, I should get this array coming out. Any questions on this matrix and the equivalent array?
I was going to ask, how do you manage that? So let's say, for example, because like surely delivery would have hundreds of food items, so you're going to have a massive, like it's basically a table, isn't it? So do you manage the table separately? How does that work when you have a new food item? How do you add it to the matrix?
Yeah, that's a deep question because it can be complicated. So in practice, we'll have a pipeline that does all this, that runs each day. And so every day on a schedule, we'll have some code that will pick up all of the items on the menu, and it will generate this matrix. And you're right, it could be hundreds or maybe even thousands of columns wide. And again, thousands or tens of thousands of rows or even more. So it's a really big matrix. But luckily computers are fast, so it doesn't matter. But for us, we're just going to look at this small example so we can understand what's going on.
Mm-hmm.
But if the menu changed during the day, then you'd have to rerun the code.
Yeah. Okay. Thank you.
Cool. So again, there's this shape method that works on arrays as well. So we can ask for the shape of this matrix, and it tells us the first number is the number of rows, and then the second number is the number of columns. That's useful to keep in mind. So that's a handy data structure for representing baskets. It's also a really useful data structure for representing item recommendations as well. The main difference here is that the recommendations have an order to them. We always want the best recommendation at the top. So instead of just having a matrix full of ones and zeros or a binary matrix, we need to fill the matrix with scores, where a higher score represents a more relevant item. So again, using our toy example, if we had these two different recommendations, we've got the chips, burger, and the drink in that order, and then drink, chips, burger. We could write this down with the top item in position 1, like this. And again, we can represent that the same way as a matrix. So the key difference here is that because the chips are in position 1 for the first recommendation, they have the score of 3, which is the highest for this example. Burger is next at 2, and the drink is in the last position, so it has a lower score of 1. And then recommendations 2, in this case, the drink has the highest score, followed by the chips, followed by the burger. The actual numbers here, 1, 2, 3, that's not important. It's the sort order of those items relative to each other that's important. So the first row could be 20, 30, 10, or 1, 1.50. As long as the way that you arrange them is in the right order, then that's a fair representation of this recommendation. And importantly, every item on our menu needs a score. So we're effectively ranking everything on the menu. Does that make sense? Cool. I'll take silence as yes.
Yeah, I think so.
Cool. So there's another really critical part of machine learning, which is performance evaluation. And this is where we want to check how well the model is working. To do this well, we do what's called data splitting. And this is where we split the data that we have available into 2 groups. One group that we use to train the model, and another group that we use to test the model. So the training set is the one that we use to develop and test ideas. I shouldn't have used the word test, but develop the model. And then the test set is the one that we keep aside, we don't look at until we're done. And then we use that test set to estimate how well the model performs. The reason that we do this is that if you just train a model and then evaluate it on the same data, it might not generalize to new data. It might have just been really, really good with that set that you've got. And then when you give it something new and unseen, it's completely hopeless. So this separation is important. This raises a question though, which is how do we actually evaluate these models when all we have are baskets? We don't really know what the most relevant item is. And the way we can do this is we can, first of all, split the data into the training and test set. We can encode the orders in the training set as a big matrix, just like we talked about a moment ago. And then for every basket in the test set, randomly pull out one item from that basket. And that's going to become our target item. So in a sense, if our model is performing really well, it should do a good job of predicting that target item towards the top of the list, given that basket that we've fed it. So I'll go through that once more because it's a bit of a mouthful, and I'll show this diagram. So we start our orders at the top. We have 20,000 of these. First, we split into training and test. A common ratio is 80-20. So we'll put most of the orders into the training set, and then we'll just encode this as a big matrix. So we've got 16,000 baskets, so there'll be 16,000 rows, and there's 39 items on the menu, so 39 columns. For the test orders, what we're going to do is have this extra random leave one out step. What this means is we'll take each of the baskets and we're going to randomly choose an item from that basket and pull it out. And then what we'll do is with the basket of items that is remaining, we'll encode that as a matrix as well. And we'll also encode the target item as a matrix. So the number of columns here are the same because we still have 39 items on the menu, but we only have 4,000 rows. And effectively what we're trying to do here is build a model that does a good job of putting this target item towards the top of the recommendation list, because we know it was related to that basket because we took it out of that basket. So we're sort of introducing this goal for the model that it can try and aim for. Any questions on that process? We won't be implementing this. I've done it for us beforehand, but conceptually, I hope kind of it makes sense that we're trying to predict something that was removed because that item is going to be relevant. But feel free to ask any question that comes to mind. Cool. Okay.
Hi, sorry, I have a question. Why is the ratio 80-20%?
Yeah, it's somewhat arbitrary in the sense that you could do 50-50 and it would still work. Usually you want to, the training process is often, I would say, more data hungry. It needs more data to work well. Whereas the testing process is a bit more straightforward and you can usually get a fairly reliable estimate with a small test set. But what you really want to have is as close to a realistic number of training orders that you can. So it's usually skewed towards the training set.
All right, thank you.
Cool. All right, so I've written some code that does this process because it'll take a little while to understand what's going on. So I'm just going to run this code, but I encourage you to have a look at it later and follow along with what it's doing. So if I run this, it produces these 3 data sets, which are the important things that we have to work with now. So we've got this X train, X test, and Y test. X train, X and Y is usually like it's a convention that we use in machine learning where we usually denote the thing that is the input as X, and then we denote the thing that is the output as Y. So X train is the training matrix X, and then X test is the test matrix X, and then Y test is the matrix of target items. So these are our 3 matrices here. We're going to use those in a minute. And you can see that the shape of them, we've got 16,000 rows in the training set, 4,000 in the test set. And this extra check was just to make sure that in every row of the test set in Y, we should only have 1 item because we randomly removed just 1 item. So the row sums, like if we add up all the numbers in each row in that data set, this one, it should always add up to 1. If we had a 2 in there, it would mean we accidentally took out 2 items. Cool. So these are the data sets that we have to work with. And then the first kind of recommendation system that we're going to build, it will be a very bad customer experience because what we're going to do is we're going to just recommend items completely at random. It sounds a bit silly. It's actually a really useful thing to do because it provides us with a reference point of a useless model. So if we then go and do some what we think is clever coding and we build a new model and it does no better than the random one, then we know that we've either got a bug or we've made some mistaken assumption about the data or the model. So this is going to be new to many people, this syntax here. So in Python, you have the concept of a function, which is essentially, you can imagine it as a box where you put some input into it, it'll do some work inside the box, and then it will spit an output at the other end. And a function is a neat way of encapsulating a bunch of logic. So this is a function that is going to take as input the basket matrix, and it's going to return a matrix of random scores with the same shape. So if basket matrix had 5 rows, that means there's 5 baskets. We need to spit out 5 sets of recommendations. So if we want a random matrix of the same shape, it's actually fairly straightforward if I remember the code. I don't want integers. What do I want? I want, I'm going to cheat again because I can't remember the function. np.random.rand. So again, the way I would do this in practice, because I can never remember all the functions, I'll just open up Google and I'll say numpy random matrix, and then I'll look up the docs and I get given this, and it says random values in a given shape. Oh, that's exactly what I want. And it'll give me an example. So I actually remember very little. All I do is plug in Google queries and get code.
Yeah, that ain't cheating. That's what I tell everybody all the time. Just let the computer do the work.
Just use all the tools you have available. I'll say that much. And then the shape I want here is the shape of basket matrix. Cool. And that's going to generate the matrix, but there's a bit of extra Python I need, which is I need to actually return that from the function. If I run this, it's not going to do anything. It's just going to define the function, which I can now call. And we're going to test the function by running this next cell. What this is going to do is I'm going to comment out this line so that we only run the first line. It will call the function with our test set. Tuple object cannot be interpreted as an integer, so I've made another mistake. It's probably the shape. I've probably specified this wrong. So I've effectively got too many round brackets in mine, I'm pretty sure is what I've done wrong. So what I need to do here is something like this, I believe. And I'm going to grab, let's just see if this works before I explain what it does. Cool. So what I got wrong there was that the result of just having shape is a tuple, two numbers together as a single data structure, but I needed to actually separate out the rows and the columns. So I took the rows from the shape of basket matrix and I took the columns from ytest. These would be the same as the columns of basket matrix, but I just did it this way to be sure that it's the right shape with the test data. What does yrandom look like now? Well, it's an array and it's really big because it's showing me these 3 dots. So it hasn't printed the whole thing out. And it's just full of random numbers. So this would be equivalent to just showing items completely at random. And we can use this function from scikit-learn, label ranking average precision score, which is equivalent to mean reciprocal rank. At least the way we're using it is. So if you remember from the slides, mean reciprocal rank is the average of the inverse of the position of the relevant item. So in English, that means that our relevant item on average was about in position 10 because 1 on 10 is about 0.1. So this is how well a random recommendation system works. And you'll see that this number will bounce around each time I run it because it is random. But this gives us a nice baseline that we can use to iterate on. And anything that we build absolutely has to do better than this. Otherwise, it's certainly not worth releasing to customers. To make this is a bit opaque, I appreciate, because you've got this matrix and you've got these numbers. What does it all mean in terms of the actual recommendations? I've also added this helper function, which will transform that matrix of numbers back into a list so that you can read it a bit more easily. So if I run that on the yrandom scores, you can see what basket we've provided. This is just sampling at random some baskets, and it will show us what items were recommended. And there's no connection at all here between the input and the output because it is completely random. Great. I'll pause there for a moment in case there are questions before I move on to the next one. And if not, I'll push on to the next part, which is our first real model. It's still going to be simple, but it's going to do something a bit more sensible. And it's going to always score items the same way. It will sort the menu items into descending order of popularity. And we're going to use the training set, remember, to do this, not the test set. So we can calculate the item popularity from the training set by summing up the values in each column, because this gives us the number of times each item has been ordered. And again, I've given you a little nudge for what I would Google to try and find out how to do that. Once you have an array of 39 item scores, you just need to turn this into the right shape, which it needs to be a 2D array with the same number of rows as the basket matrix. So I'll show you what this would look like. Actually, I'll do this in a separate cell just to show it step by step. If I were to do, so np.sum, that is a function provided from the NumPy package. If I were to ask for the sum of the xtrain array, gives me one number, remembering that xtrain is a big matrix. So what this is doing is it's adding up every number in the matrix. If I add this extra argument, axis equals 0, now it adds up every column, which is exactly what I want. So every number in this first column adds up to 1, second column adds up to 6,000, and so on. If I change this to 1, I would get the row sums, but I want the column sums. So I'll do axis equals 0. And then I'm nearly there. I just need to make it the right shape. And there's a handy function called broadcast2. Broadcasting in NumPy is not like broadcasting a radio station. It's taking an array of one shape and spreading it out into a different shape. So if I were to, for example, take this array, and if I were to broadcast it to the shape, let's say 3 rows, 39 columns. And again, I may have done the syntax wrong. Let's see if I get an error. I got it right this time. So it's the same array repeated 3 times, 1 for each row. So we're going to use that function here, and we'll broadcast it to the shape of basket matrix. So I'll just ask for basket matrix dot shape, and hopefully it won't complain, but we'll see. It has indeed. I didn't actually return this. Yeah, can I just double check how an array is different to a list tuple? Just a question in the chat. That's a good question. So an array is different to a list tuple. So a list just looks like this with a single dimension. A tuple is very similar, looks like this. The main difference between list and tuple is that a list is mutable, which means you can change its elements. A tuple is not, it's fixed. And then the array is sort of like a generalization of the list, in that you can still have a very similar data structure, but the array supports a lot of useful linear algebra operations, and it supports arbitrary dimensions. And what I mean by that is you could have, this kind of thing where you've got an extra row. And I know you can do the same with a list. Like you could have a list that looks like that. The difference internally is that this array is going to be much more efficient when you do things like array multiplication, summarization, transposing. But one limitation of the array is that it has to be like every row has to have the same number of elements. It can't be like, if I try to do this, oops, and just have 2 elements, it gives me a warning because I'm trying to create a ragged array, which is not the same length in each row, which you can do, but it's a bit messy. but conceptually a list can be very similar. But I hope that helps sort of explain a few of the differences.
So, sorry, I've just come on. I've unmuted. Just to double check. So, is it also that basically you can turn it into a matrix? Is that how it's quite useful?
Yeah, exactly. And then you can do all of the matrix algebra. So you can do matrix multiplication and so on.
Okay, awesome. Thank you so much.
Cool. So hopefully that fix will now give us something sensible here. And yeah, indeed, we've got a reciprocal rank of 0.34, which is quite a lot better than the 0.1 of the randomly ranked items. So straight away, just by recommending what's popular, we're doing much better. And we can have a look at a sample of output from that. And now you can already see that there's still some problems here. Like if I've got a deluxe cheeseburger, I probably don't want another cheeseburger. And all of these recommendations are the same because we're ordering them by popularity. And that's not going to depend on your basket. So it's an improvement, but it's still a bit basic. So this one, I appreciate how much time have we got left? Oh no, we've got plenty of time. I thought we were finishing at 8, but we've got a bit more. So this one is a more challenging model, but it's one where we'll actually start to see more intelligent and varied recommendations. So instead of always recommending the same thing based on popularity, we're going to use information about how often items are purchased together, or the co-occurrence, to generate recommendations that are different or potentially different depending on what you've got in your basket. So I'm going to illustrate the idea of co-occurrence first. So here's that pair of baskets we saw before. We can construct from this what we call a co-occurrence matrix. And this is a square matrix that has each row and each column is an item. So it's always the same number of rows and columns. And it counts the number of times pairs of items appear together. So ignore the diagonal for a moment. Focus on this one in position, the one I'm hovering over. Burgers and chips have been purchased together only in basket 1, so that gets a 1. The burger and the drink have been purchased together twice, so it has a score of 2. And then the chips and the drink have only appeared in the same order once, so they get a 1 there. And you can probably see that this matrix has to be symmetric because the number of times burger appears with drink is logically the same thing as the number of times drink appears with burger. And we choose to set the diagonal to be 0. We just decide that we don't want items to co-occur with themselves because it doesn't really make sense for what we're trying to do. Before I go on to the next part of this, any questions on what the co-occurrence matrix is representing? Great. So makes sense. Thank you. So we need to construct this matrix for this model to work. And if you've had some exposure to Python before, you might be tempted to write some loops, and you could definitely do that. You could write a loop that says, let's loop over these baskets, and for every basket, let's count up all the different pairs of items, and we'll increment the numbers in this matrix accordingly, and then we'll move to the next basket and do the same thing. That would work. That would definitely work. But what I want to share with you all is a bit of linear algebra, which comes back to your question here and about arrays. So if we use these matrix and array formats, we can calculate the co-occurrence matrix in a single step, at least in code, by taking the transpose of the array and multiplying it with the array itself. The transpose is basically what you get when you take the array and you take every row and you make it a column. So you're kind of like flipping it almost. So you can see that the first row of our basket matrix, so this is the basket matrix, it will look the same as this. The first row becomes the first column, and the second row becomes the second column. And I won't go through all of the linear algebra because it's a bit dry, but if you were to look up matrix multiplication, you could follow through this logic of how this arises out of this operation. And then we zero out the diagonal and we get exactly the co-occurrence matrix that we want. Once we have that matrix, that's essentially the model, by the way, is this big matrix of co-occurrence. We can then score the items. And the way we would do this, if we did it iteratively with loops, is we would say everything that the user has in their basket at the moment, read off the corresponding row in the co-occurrence matrix and increment the score of every item with the row's values. So to make that a bit more concrete, if, for example, I was building a basket and all I had in that basket at the moment was a drink, nothing else, the way this model would score items is it would give the burger a 2 and the chips a 1 and the drink a 0. And that would be the score of the items. If I had a drink and chips in my basket, it would do, it would still give the burger a 2 from the drink, but it would give the burger an extra 1 from the chips because they've been brought together once before. So it's effectively like adding up the rows for each item that's in your basket. So in the case where you'd have both of these, burger would have a 3, chips would have a 1, drink would have a 1. Conceptually, that's a bit weird because why do we give chips and drink a score when they're already in the basket? Again, this just comes back to the fact that we have to give every item in the basket a score, on the menu a score. Yeah, there's a question.
Yeah.
Hiya, it's me again, sorry. So can I just check? So does that mean that basically the higher something scores, the more likely it is to be recommended?
Yeah, so when we come to the actual recommendation,
Right.
we're going to sort the items in descending order of score. And that's what we'll show people.
Can you
Awesome.
repeat what you said about that? Sorry to interrupt whoever that was. Can you repeat what you said about this, how the scoring works again, the concurrence?
For the co-occurrence, so the way the scoring works is for every item in your basket, it will look up that row in the co-occurrence matrix. So if you had a burger in your basket and you want to know what the score of the chips are, then it reads it off from the matrix. It would be a 1 and the drink would get a 2. So it would just be this row here would be the scores of the items if all you had in the basket was a burger. And likewise, if all you had in your basket were chips, then the scores of the items would be this row. If you had both of these items in your basket, the scores would be the sum of these rows.
Oh, okay. Yeah, that
So,
makes sense now.
yeah, you can kind of think of it as like, for everything that I've got in my basket, how many times has everything else appeared with it, if that makes sense.
Yeah, it does.
Cool.
Thank you.
Great. Any more questions on that? I want to come back to that question about what actually gets shown to the customer, because that's important to understand. So the output, if I go back to one of these models, like the random ranking one, if I print out what y at random looks like, then these scores represent our best guess of how relevant each item is. It is a guess, but then when we actually serve the recommendations, what we do is we take these numbers at face value and we say, you know what, this is our best guess. This one here is pretty high. I'm assuming it's probably near the highest. There's a whole bunch I can't see because it's too wide. But if these were all items that we had, then this one here would be in position 1. And then this one here would be in position 2. So these scores define the sort order of the final recommendations that get served to a customer. But they are items. Yep.
Sorry, so these orders, so is it that the closer it is to 1, the better a recommendation it is?
So is your question about these numbers?
Yeah, those numbers.
Yeah, so in this case, the actual like scale of the numbers is not important. So these could be like all multiplied by 100. The higher the number though, the better we think it is. And
Right.
then the next, if I were to comment this out again and come back to the label ranking score. What this does is it takes these numbers, these predictions, and it compares them to the test set, which is those items that we randomly pulled out. And so it's basically asking the question, given those scores, what position was the target item in? So if in that big array of random scores, for this example here, the drink had the highest score, that would be a perfect recommendation. But with a random recommendation, this drink is going to be anywhere. And in fact, on average, it should be in the middle of the middle of the set of items. So the score that we get from this label ranking score is the mean reciprocal rank, which is, if I come back to this, it's this number here. So I'm hoping that might help clear up the connection between the array of scores and then the single score that we get after this process.
Can I just check, because you're asking, is it closer to 1? Are you kind of thinking in terms of probability? So yeah. Okay. So it's so kind of it's the relationship to probability and the rank, isn't it? I mean,
that's a good connection to make, actually, and I hadn't thought of it that way. Yes, in practice, often these scores will represent a probability. And in that case, if it was 0.5, then we could interpret that as a 50% chance of that item being relevant. It depends on the model type. All we need to make a recommendation is that ranked list. But to make a really good recommendation, it's often helpful to have a model that predicts the probability, because then you can combine that with other information, like the price of the item. And if you take the probability and the price and you multiply them, that gives you the expected value of showing someone that item. So yeah, I think your question was actually reflecting more deep thinking than I realized, which is the connection to probability, which is a really good one to point out.
Okay, cool. Thank you. Thank you so much.
Great. So we're on the co-occurrence model. And the way in which we make predictions I just described in kind of like a sequential, logical way, where you start with what's in your basket and you look up the array. But just like we could construct this matrix with a bit of clever linear algebra, you can also generate the scores with some linear algebra. In this case, once you've got the matrix, it's simpler than before. You just take your basket matrix and you multiply it with the co-occurrence matrix. And that gives you the array of scores. So if you're still following along, please continue. I'll try and implement this one now. So remembering we need first to generate the co-occurrence matrix from the training set. It's the transpose multiplied by the basket matrix itself. So there's a function so we've got xtrain. I think you can just go .t, yeah. That gives us the transpose. I'm hovering over it because sometimes when you hover over it, it gives you the docs. Oh, here we go. Get the transposed array. That's exactly what we want. And then what we want to do with that is multiply it. And there's a function np.mult multiply. And we're taking, come back to this, the transpose multiplied by the matrix itself. Matrix multiplication, unfortunately, is not the same as multiplication of numbers, in that 2 times 3 is the same as 3 times 2. If I were to flip these, I'd get a different answer. So the order matters here. That gives me the co-occurrence. To actually score the items, though, we need to take that matrix and multiply it with the basket matrix. So basket matrix co-occurrence. Again, there's a good chance I've made a mistake. Let's see what happens. Yep, that's good. Of course. So what have I got this time? Operands could not be broadcast together with shapes. This is a interesting error because it tells me something about the shapes of the arrays I'm trying to let's go through this error actually, because interpreting errors is a really useful skill. So it's a value error. That usually means there's some kind of mistake with how I'm putting like incorrect values into functions. They don't make sense. And it's on this line where I'm calculating the co-occurrence. Where I'm scoring the items. So this is like a stack of a call stack of the sequence in which the error happened. So you can see this is the line that I ran here. And it called that, and then it went into this line, and it's pointing me to the line with the error. So this line is problematic. And what am I doing wrong? So operands could not be broadcast together with shapes. So I'm probably doing xtrain. I'm gonna again cheat and see what I came up with earlier. And I haven't got my solution, so I'm gonna have to actually solve the problem. So what have I done wrong here? If anyone has ideas, shout out, by the way. I'm gonna have a think for a moment. First of all, I might isolate this line and just confirm that it is, in fact, what's causing the problem. And yeah, I get the same error, so I know this is where I'm going wrong. Let's just check the shapes of these things. So what do I get when I ask for the shape of this? So it has 39 rows and 16,000 columns, and then the n and the shape of xtrain. It should be okay. I can guarantee I'm doing something very, very silly. And what I'm going to do again is go back to Google and say NumPy co-occurrence. And if you've done any Googling of programming problems, I'm sure you've come across Stack Overflow before. Do you ever use chat? Yes, absolutely. I do use ChatGPT to debug. I only started using ChatGPT to debug like within the past few months. And that might be fun to do. So before I think all I've done wrong here is np.multiply, I think might actually be doing element-wise. Yeah, that's it. I reckon if I were to go to this cheat sheet for NumPy, I'll show you what I mean. I think I know exactly what's going wrong. And if I have a look at np.multiply, multiplication, it doesn't actually tell me whether it's multiplying the whole matrices or whether it's doing element-wise multiplication. I'm going to assume it's doing element-wise. And what that means is that the two matrices have to be the same shape. So let's get this working first, and then I'll come back to debugging and ChatGPT, because I think that would be a fun thing to try. So let's go back to here. I think all I need to do here is do a dot instead of a train. Sorry, instead of a multiply. And I might need to do the same thing on the second line. Yeah, in this case, see how the arrows moved? So line 3 works just fine now. So I think I need to use the dot product and not np.multiply. This is a very rookie error. For me, at least, I should know better. With any luck, I'm hopefully still doing the right operation. Okay, I'm nearly there. This is interesting. It worked. It didn't give me an error, but it's actually given me a worse mean reciprocal rank score than the popular items model, which was 0.33. And the thing I forgot to do here was this step, 0 out the diagonal. So the problem here is that I'm going to be giving every item that's already in the basket quite a high score, which is not going to be very useful. So I think there's a function set diagonal or diagonal by set diagonal. Fill diagonal. Let's take this. I need to specify the array and then the value, not just call it on the array. So I think I need to do np.fillDiagonal co-occurrence of 0. And hooray, we get both code that runs and we get a score that's even higher than the popular items recommendations. So we're actually learning something useful here by looking at co-occurrence. And if I print some recommendations out, then we can start to see there is a bit of variability here. So if you've got a cheeseburger, you're going to get different recommendations to if you've just got a shake. In this case, the shake goes with cheeseburger, deluxe cheeseburger, small fries, and so on. So that was a very realistic depiction of what programming is like with this stuff. You always make mistakes and you keep iterating. I'll come to ChatGPT now, but before I do that, are there any other questions? No, that's great. If something comes to mind, yeah, but it happens all the time, and I've been doing this for like years and years and years. So, what am I looking for here? So I've got my Zoom windows blocking this. I can't read it. So we've got like a kind of Deliveroo approved ChatGPT interface, so they make sure that we're doing things sensibly. Has everyone played with ChatGPT before, whether it's just for writing silly poems or for code?
Yeah, I'd love to see hands up on that.
Not yet. Yes.
Yeah. 1, 2, 3.
Yeah.
Not for code.
Okay. Yeah. It's definitely out there.
Yeah. This is going to be popular.
Yeah.
I don't think we've done a session on that yet. This could be a whole session in itself.
Oh yeah, absolutely. So what I might do is I'll reintroduce that error and try to undo this. I'm really glad you asked this question actually, because sometimes I forget to actually use ChatGPT for stuff like this, and it can be quite quick. So what I'll do, it'll be interesting to see if it can figure out what the problem is if I just give it this and not what xtrain actually is. Like it might need that context as well. But let's just see what happens if I give it the function. Can you tell me what's wrong with this code? So I'll give it the function, and then I'll give it how I tried to call it. And then I'll give it the error. I'm still learning how to use ChatGPT effectively, by the way. So see what happens. Text contains personal information. I don't think it does. I'm just going to scan through it. No, it doesn't. zip code. Has it copied that? I don't know why it's replaced that with zip code. I'm just going to leave it as is and see what happens. The error message indicates that there is an issue with the shapes of the arrays being multiplied in the score items by co-occurrence function. Specifically, the shapes of xtrain.transpose and xtrain are not compatible for element-wise multiplication. So that's what we thought the problem was. To fix this issue, you need to ensure that the shapes of the arrays are compatible for multiplication. So it's giving me a solution, but it's giving me a solution to the wrong kind of root cause, if that makes sense. It's assuming that I actually want to do element-wise multiplication, which is a pretty reasonable thing to assume based on the error message. Well, first of all, that's pretty amazing that it can even do that. But in this case, what we would get out of this is, I'm pretty sure, the wrong thing. So let's see what happens if I try their solution. Yeah, so the problem now is that the okay, so it didn't. Yeah, it doesn't know what the shape of basket matrix is because it replaced these things with the word zip code. I don't know why it did that. But I reckon if you were to repeat this, but you were to give it the context of what the matrix is and you were to paste the error message in properly, I reckon it probably would give you the right solution. But you do have to proceed with caution because sometimes it will give you a wrong answer with high confidence and that can be dangerous. So it's a very useful tool, but it's not quite smart enough to replace us just yet. Maybe later. But yeah, great question. So I'll leave that in a slightly broken state for now, just to move on. So I left this extension exercise in here if people want to take this even further in their own time. So one problem with all of these solutions that we've talked about so far is that they have no penalty for items that are already in your basket. So somewhere in like this recommendation list, probably not at the bottom, you might find shake. Well, this is probably a bad example because there's only one item in the basket and we know the co-occurrence of shake with itself will be 0. But if there were 2 items in the basket like this one, see how it's put fries. It hasn't got large fries in the top 5, but I reckon if you were to print out more than the top 5, you'll find large fries in there, whereas really large fries should be at the very bottom of the list or not on the list at all. And in fact, in practice, what we do in the app is we never recommend the same item in your basket. But for the purposes of evaluation, you might want to try and fix that. There's also an association rule learning algorithm. That's a more powerful technique than just simple co-occurrence. And then another thing I wanted to point out is that in practice, we have access not only to baskets, but we also have access to recommendation impressions. And what I mean by an impression is this information here on this slide. We know what items people saw and we know what items people interacted with. So if you've got that knowledge, you don't have to do this process of randomly pulling items out of baskets. You can actually just say, well, what were they presented with and what did they interact with? And that will be a more useful objective to try and learn, train a model to perform well against. And if you've done like a data science beginners course, you've probably heard of classification or regression models, and then you can use all of those models for ranking. So I just left this in here for people who want to take it further. And that's it from the workshop point of view. I'll flick back to the slides just to summarize what we've covered. I've also left in here just a few links to resources that you can use to learn a bit more. I'm really glad that all of you stayed to come through all of these exercises, even though many of you have no experience or very little experience with Python. I'm really, really pleased that you found it interesting enough to come through. And if you want to learn more, you can definitely go through these. And if this has sort of maybe made you a little bit interested in a machine learning or data science kind of role, then there's this more sort of beginner-friendly overall course to machine learning, which I'd recommend as a better starting point than any of these resources. Recommender systems could be considered a fairly advanced topic because it combines a lot of different ideas from other sort of ideas in machine learning. So I'll jump back to here just to finish up with the slides. Yeah, so we learned that recommendation systems are all about suggesting relevant items to users. So we touched upon the two paradigms, content and collaborative. One that uses what we know about items and their properties, and the other that uses what we know about the people who interact with them, and then comparing items through those interactions. Quantifying performance is critical. There's mean reciprocal rank, that's one rank-based measure, but there are others that you can look up as well. If you Google learning to rank, you'll find a whole bunch of different ways of quantifying this. And then the simple baselines are really important as well. And they can be surprisingly effective sometimes too. So don't sort of write off a really simple solution as a starting point if you're in a technical role and you're trying to build something for the first time. And then hopefully maybe I've convinced someone here that linear algebra is cool, but we'll see. That's more about like what you can do with loops. You could do potentially much more simply and succinctly with a bit of linear algebra. So that's all I have for this evening. Yeah, but I'm very happy to stick around and answer questions about this or anything else that's on your mind, or go back to the code and talk about that as well. So
yeah, definitely. Thank you so much. I mean, who knew 7,000 cheeseburgers and so much to kind of think about how, in terms of actually why different things are chosen together. Johan, you've got another question?
Yes, I just wanted to check with Callum, basically, because I'm guessing that a lot of us are quite new to coding or to tech, or career switchers. Do you think that like machine learning is so advanced that like some of us couldn't just go straight into it off the bat? Do you think it's something that, you know, would require quite a lot of time? Just curious on your thoughts on that.
yeah, one of my favorite things about machine learning and data science in general is how many different kinds of people there are in terms of their professional or academic background. So, for example, I studied mechanical engineering, which is sciencey. I did a bit of computer science as well, but I went from an applied engineering domain into data and then into machine learning. I think I see where the question is coming from. I think it could be potentially challenging to find the right entry-level role if you're coming in, let's say, from a completely different field, like a career switch from something non-technical to technical. But I don't want to say it's impossible and discourage people either. So I think if you're looking at that kind of a switch and you're really interested in machine learning in particular, I would keep an open mind about roles that bring you closer to it without necessarily jumping into it in a direct step. So for example, if you were a data analyst in a tech company, then you'd be in a really great position to get exposure to the science teams that do some of the machine learning. And that could be like a good stepping stone. That said, like, you could just be an analyst and that could be a amazing career path in and of itself. So it's definitely not like data science, machine learning, analytics, data engineering, one is harder than the other, because you can be at the top of your game in any of them and be equally challenging. But I think if you're considering machine learning in particular, yeah, you could make that switch, but I'd say think about all the different options you have to try and get into that, and don't be discouraged if making a direct leap is really challenging, because it took me many years to actually get the machine learning engineering title, but many of my jobs along the way, I picked up lots of useful skills to get there.
And don't forget to kind of look at training and use that to build your GitHub profiles. People have, especially if there's areas of data or areas of technology you're interested in that you think machine learning could be applied to, just build your own portfolio. Because actually, I've heard of people getting jobs just because they took on they just followed a thread of something they were interested in, and just worked their way through kind of solving a problem that other people haven't solved. So there is kind of just the job route, but there are also kind of training resources, and kind of look for mentors. There's lots of ways in.
Awesome. Thank you, guys.
Yeah. That is a great point as well, Mary. I'm glad you raised, because yeah, that Coursera course, that's the way I started as well. And yeah, building up a portfolio of something that you're genuinely interested in. So applying data science or machine learning to something that you're passionate about is a good way to make it more easier to motivate yourself to keep going.
And kind of find peers as well. Part of being part of this network. Put a message in the in some of our forums, and just see if there's other people that want to go on that learning journey with you, and kind of work together to build your skills. That's another approach. I actually had a question. I was wondering a bit more if there was more you could tell us about this bias towards simplicity idea, and how you approach that in day to day, and how you use that as a mindset.
Yeah, definitely. So in terms of how we bring that sort of bias to simplicity to life, one way is definitely if we're exploring an opportunity in a new area. So let's say we wanted to change the way that we rank something in the app. We would really challenge ourselves to think of the simplest possible implementation that is a step in the direction that we want to go in. So if our goal is like, let's be super personalized, let's take into account everything we can think of, like the time of day, what people have ordered in the past, that's a great sort of end goal. And we'll think, given the current state, what's the smallest step we can make that moves us in that direction? And then we'll take that idea forward and we'll do an experiment with it, and we'll learn something from it. And then that will help motivate further iterations, or sort of course correct, and we'll change our approach. But often data people, myself included, we're very tempted to like build the best solution possible straight from the beginning. And often what's more important is to build something that's good enough that you can do quickly and learn from.
That's very much like the concept of MVP, minimal viable products, that kind, and lean methods that would be worth looking up as that for that approach.
Yeah.
Oh, I've got a question. What forums would you recommend to find learning buddies? If you go onto our community forum, you could just kind of post a message that other people might see, and see if, but also anybody on the group here, if you kind of like get in touch with each other, share your LinkedIn profiles or something like that. Those are ways that you can connect. Any other questions? Nothing more at the moment.
If other questions come to mind later, feel free to reach out to me, connect on LinkedIn or all of that, callum.webb@deliveroo. If I can help, I'll be happy to.
Okay, amazing. I mean, that was fantastic. The opportunity to kind of do a live walkthrough like that, you know, I can assure you that's a really, really difficult thing to do, and to kind of do that on the fly like that. That was so yeah, everybody's really appreciating it. Thank you so much. And yeah, people are really keen to kind of follow up and find out more. So that's great. Really, thank you so much. So I think we'll end the call there. A big thank you to Callum, and if you know kind of continue wanting to work on the collab, I'm sure if you really get stuck, you can send Callum a bit of a message, or if there's any other questions, just let him know. Thank you so much, Callum.
Thanks, Laura. Have a good one.
Bye.
Thank you. All right.
Thank you.